The VIC-20 build's nearly complete, and we're finally at the stage where we can play some classic games. Qbert, check. Radar Rat Race, check. But Choplifter, not quite. Something's missing, a vital piece of the puzzle to unlock the machine's full potential. You see, Choplifter uses a mode that pushes the VIC-20 beyond its default capabilities. To bring this classic to life, we'll need to implement bitmap graphics, a technique that essentially allows us to take control of every pixel on the screen. In today's video, we'll explore how the VIC-20 handles bitmap graphics and how to adapt our build to make it work. By the end, we'll not only have Choplifter up and running, but we'll be on our way to unlocking the full graphical power of the VIC-20. Let's dive in. First, I've been able to get this transparent bread bin case from RetroFusion, which is really cool, but it does constrain the amount of space I have on the perf board. So, I glued the main board and the soundboard together and moved some chips and connectors around to make space, which I'm sure I'll need. Earlier in the series, I used a 4:1 multiplexer so I could interleave CPU access with video access. Remember that while CPU clock's high, the 6502 has unfettered access to the main memory, while CPU clock's low, I need to do a character read, a color read, and a bit mask read. To generate these addresses, the lower bits come from the raster generator and the value read from the character address. But originally, I hardwired the upper bits of these addresses directly on the 4:1 multiplexers, which you can see here. But these upper bits are actually programmable in the VIC chip. These address bits mainly come from the register at address location 9005. BV is the video matrix address, bits 10 through 13 are stored in 9005, and bit 9 is stored in the top bit of the register at 9002. I've shadowed the data at these addresses with some 74HC574s, and some of these bits feed directly into the address multiplexer. BC is the bitmap address. Again, bits 10 through 13 come from the register at 9005, and 3 of these bits are used to form the overall bitmap address. Interestingly, BC13 needs to be inverted, because the value of 0 is used for the ROM-based character generator, which is located at 8000 hex. When BC13 is set, it actually addresses the inbuilt 5K RAM starting at location 0. This is all wired up and running, and this mapping is how we got Qbert and Rat Race running. When we try Choplifter though, it just doesn't work. Just as a general rule, it's easier to write some games if we have a bitmap display. That's at least 1 bit per pixel, but in standard display mode on the VIC-20, we only have 256 definable characters, but at 22 by 23 characters on the display, we have 506 defined character locations. This means we have nearly double the number of character locations compared to programmable characters, and we can't define a bitmap display where each pixel can be independently defined. So, how does Choplifter work? Let's take a closer look at how the VIC registers are programmed. First, how come the display is 22 by 23 characters in the first place? I've broken out the 2 VIC chip registers here located at 9002 and 9003 hex. In standard mode, where we run basic, let's see what's going on with these registers. 9002 holds 16 hex, which is 22 in decimal, which might be the number of columns. (9003) holds 2E in hex, which is 46 in decimal. Interestingly, 46 is double 23, which is the number of rows. Let's see if we can make sense of this. Sure enough, the lower 7 bits of 9002 are for the number of columns, and bits 1 through 6 of 9003 are for the number of rows. Because we start at bit 1 instead of bit 0, we know that 23, which is 170 in hex, shifted left by 1 position is 2E, which is all good. But now, let's see what's happening with Choplifter. The register at 9002 is 96 hex. If we chop off the top bit at 16 in hex, which is 22 columns, which is basically the same as before. But now, 9003 has 17 hex. If we shift right by 1 bit, the number of rows is B hexadecimal, which is 11 rows. 22 by 11 characters. That's a bit odd. And why is the bottom bit set? Looking at 9003, we can see the bottom bit as the D value. What's that? That makes sense. This is the double-sized character bit, which means the characters are now 16 scan lines high, but still 1 byte wide. Now, here's the real secret behind games for the VIC-20. We have 22 by 11, which is 242 characters on the display, yet we still have 256 programmable characters. So each character displayed can have a unique bitmap. That's how we get bitmap graphics. There are a couple of ways to deal with this, but how does Choplifter specifically handle it? We noticed before that the 9002 register contained the value of 96 hex, and we know that the top bit is BV9, which is part of the base address for the character map. We know that the rest of the address is stored in 9005, which is this register here, so let's see what value it takes. HC hexadecimal. So, by my calculations, the character map will be located at 200 hex, and the bit mask will be located at 1000 hex. As a result, this is what the memory map for Choplifter looks like. We have 256 bytes for 0 page, 256 bytes for the stack. Most of the page at 200 hex will be the character map, and the 300 hex page will be for temporary storage in the game. Most of the memory from 1000 to 1 FFF hex will be for the character bit masks. This is actually the primary reason why I think the VIC-20 came with 5K of RAM. It's really the minimum required to do bitmap graphics for a game running off a cartridge located at 8000 hex. I suspect this was the money configuration they had in mind when designing the system. Okay, you might be saying, but how does this make a bitmap graphics display? Well, there are a couple of ways to do this, but this solution I'm about to go over is pretty easy. We have a 22 by 11 grid of characters. If we start with character 0 in the top left, then increase the character number as we go down. Remember though, the VIC chip expects the data in the character map to be in row order, so the next character down is located at 216 hex. The start of the next column will be character 11, then 22, and so forth. What this means is that the region for this first character will be located at 1000 to 100F hex. For the second character, it's 1010 to 101F, then 1020 to 102F, and so forth. Each row of 8 pixels within a column will be stored in contiguous memory locations. For any given screen pixel located at XY, the address of the byte containing the pixel will be x divided by 8 times 11 plus y plus 1000, which is the base address. The x offsets in the base can be stored in a lookup table, and y can be an index register. Voila! Bitmap graphics at 176 by 176 pixels. Okay, this is good, but now we have another problem. In double height character mode, we have 16 scan lines per character, then the character code, so the character data in the address is shifted left by 1. Let me show you that again. 16 by 8 characters, and 8 by 8 characters. By this stage of the build, I'd started to get a bit locked in, but I did have a spare 74HC574 wired onto the W bus. So I'll just latch the character into 2 registers and have the outputs offset by 1 bit position. This means I can just use the output enable to select the one I want. I'm still left with the problem of the least significant bit and the most significant bit, and I can get around this with a single 74HC257 2-to-1 multiplexer. Enable 16 is just the bottom bit of the 9003 VIC chip register. Let's go to whirl. Now that's much better. I'll play a bit further and see how we go. I actually played Choplifter on my own VIC-20 back in the 80s, so this is pretty satisfying. We've got everything but the explosions. Let's see what we can do about that. The next part of the design is the noise channel. From reading the forums, if you don't get this exactly right, it sounds okay, but it doesn't sound like a VIC-20. It's pretty hard to get all the details on this part of the circuit, and my first instinct on how to generate this was completely wrong. Ultimately, I chased down some forums and even asked ChatGPT about how the white noise generator worked. I also looked at the code in the VIC simulator just to make sure I understood what was going on. Much of what I'm about to present was figured out by Lance Ewing, who reverse engineered the die photo of the PAL version of the VIC chip. We start off with the pseudo-random number generator, and if we tap off one bit, it should be white noise, and this is probably what I would have done to make the noise generator. The problem is that there's equal distribution of the energy across all frequencies, meaning that the high-frequency sounds are as loud as the low-frequency sounds, which is perceived by humans as being harsh and grating. If we reduce the amplitude of the high frequencies, it's more tolerable to the human ear. To solve this, the VIC-20 uses a form of a digital low-pass filter, which I'll discuss in a moment. We'll start off with the pseudo-random bit sequence generator. Generating random numbers is a whole discipline unto itself, so I'm only going to skip the surface here. For years now, when I've needed random numbers, I've used an adder with two registers to generate a sequence of pseudo-random numbers. We have two registers that both feed into an adder. We feed register A into register B, and the sum product goes back into register A. We tap off some low-level bits from the sum output, and this is our random number. If I seed the registers with 1 and 0, then this circuit will actually generate the Fibonacci sequence, but generally I seed them with two large prime numbers. Ultimately, this is just another finite state machine, but we want the cycle period to be as high as possible, hence the use of the prime numbers. The VIC-20 itself actually uses a simpler form of pseudo-random number generator, which is good for generating one bit at a time. It's called a linear feedback shift register. It taps off various bits to figure out a new least significant bit, then it shifts the value in the register left and inserts the new least significant bit. Again, this is a form of a finite state machine. Ideally, we want this combinatorial logic that calculates the next bit to contain at least a few exclusive OR gates, so that on average, we'll produce an equal number of zeros and ones over time. This is the linear feedback shift register that the VIC-20 uses, and tip of the hat to Lance Ewing who figured this all out. I'm not sure I'd have the patience to do that. One of the main issues for any pseudo-random number generator is its periodicity. Now, the VIC-20 linear feedback shift register has an enable input. When this is low, the shift register will eventually fill with ones. I've written some code to test the periodicity of the design with the seed value of FF hexadecimal. The periodicity was 65,535 clocks. The only value not touched is 0 hex, which kind of makes sense. If the LFSR contains 0, the output of the exclusive OR gates would be 0. This feeds into the shift register and maintains the 0 that's already in the LFSR. Here's the schematic diagram for the linear function shift register in the pseudo-random number generator. Instead of using some dedicated shift register chips, I've used a couple of 74HC574s where the outputs are wired up to the inputs, but each output is offset by one position. This requires more wiring than if I'd used, say, a pair of 74HC595 serial in parallel out shift registers. But I don't have any on hand, and I figured by the time I ordered them and waited for them to arrive from China, it'd just be simpler to wire up the individual bits of the 74HC574 pair. The second part of the noise generator divides the signal from the pseudo-random number generator by 16. Although this isn't completely obvious given that it's wired up as a shift register. But we can see that it requires 16 clocks to complete a cycle, so I suspect this could have been done with a resettable 4-bit ripple counter. This shift register can be wired up with a single octal D-type flip-flop chip. I'm not sure why they did it this way, but maybe 8 flip-flops without reset use fewer transistors than 4 flip-flops with reset. If you know the reason, leave a comment. Here's the schematic for the divide by 16 filter. I'm going to use a regular 74HC574 octal D-type flip-flop chip instead of the shift register chip. I'm wiring up the output filter. I'm starting to get a bit low on real estate on the board. I figure I've still got space for 5, maybe 10 chips if I can push it, and I'm going to use that for generating the logic to handle the different screen resolutions, which really is the last challenge. This analysis of the noise channel is my best guess to date, but it's not well documented. If I've made an error, let me know and I'll correct it in the next video. I think I'll end this video here. I also need to connect up the volume control for the audio, so I'll test and debug the sound channel fully in the next video.